I guess that's my cue to jump in and get started. Let me just take note of the time here. Okay, so 12:55. Um, so we're going to jump from um, school to work, and I'm going to do my best to make that transition as gentle as possible. But my talk today is going to be centered around application of this kind of data for solving problems in the electric utility, and it's going to draw from the work that's happened at Dominion Energy over really more than a decade at this point, with a focus on the last couple of years of work as we've become more competent in our use of data at scale. So I'm going to try to reframe this. I presented this content before in other venues, and I'm going to try to reframe it in two ways. One is what are the lessons learned for folks that are moving in the direction that my team has moved in. What are the things that they need to keep in mind as they progress, and what are potentially some of the things that they should avoid? How should they think about these things strategically and organizationally? And then the second is some really interesting case studies where we've been able to exploit our Synchrophasor data and data analytics platform to do some really interesting things. So with that, I'll jump in. I alluded to the fact that we've had a very long history in synchrophasors, we as in Dominion Energy, but also me personally. The story begins for Dominion and me in the exact same year. My very first semester of grad school, I was indoctrinated into the world of synchrophasors back at Virginia Tech, and have really watched it evolve both at the community level and at Dominion over that time period. And I'm going to make an assumption that there are some young folks, or, well, I guess I'm technically still young-ish, but some younger folks on the call. And I know that we live in a world of constantly changing job titles. We move from one role to another, and I would challenge you to find something that you can do, even if it's across multiple jobs, but something that you can be a part of for 10 years. Looking back at a decade of your life and seeing that kind of transformation is really special. So I would really encourage you all to do the same. But in terms of Dominion, there's a few key points I'll make before we get into some of the details. One is the DOE was really, really helpful in catalyzing our work with synchrophasors at Dominion. The second thing is we've got a lot of PMUs. Now, it took us a while to get there, but we have nearly full transmission system coverage with synchrophasor measurements in many of those ways that those measurements are redundant, meaning we have the same measurement from multiple devices. And to put a number to it, we have approximately 40,000 individually measured physical quantities. That includes voltage phasors, current phasors, frequencies, digitals, all of those things. And as you can imagine, the path forward wasn't very linear, and we'll talk about that in a moment. But in the last few years, what we've really done is taken all of that data and really challenge ourselves to find a meaningful return on investment from that. So, but I'll start with a story from 2017. We did all these really great things, and we had all this data, and we'd made a lot of assumptions about how we were going to manage it and how we were going to use it that had really never been stress tested. And what ended up happening was that we found out very quickly that our enterprise data historian just wasn't up to the job of not only ingesting, not only visualizing and analyzing our synchrophasor data, but sometimes just ingesting it itself. And we put together a plan, and the plan was for a number of reasons just very silly, and couldn't guarantee us at the end of the day that we would actually be able to do any real analysis on large volumes of historical data. And so this required us going back to the beginning, and really try to think about this problem from first principles up. So we realized very quickly that this problem of working with high resolution time series, which synchrophasors really are sort of the first class of data that falls into this category for the utilities. Certainly you have event waveform data, but they're so small in nature, even the density doesn't become a problem. But like continuous high resolution time series is a very special computer science problem. And even the best technologies that exist out in the world, made by some of the household names, the Googles and the Amazons, were not designed for this kind of problem either. And so at this time, I took it upon myself to really understand, well, why in the heck is this so hard? Why can't I work with the data the way that I want to work with the data? And it led me to find a startup company who, now I guess are based out of Washington, D.C., called Ping Things. They're the prime on the NI for AI project that we're here talking about today. And they're the ones that built the technology that we ultimately ended up using to find a home for our synchrophasor data. So all that being said, we needed the right tool for the job to be able to push our use of synchrophasor data forward. And the way that we sold this internally was with a very simple concept that basically our use of data was burdened by the cost of experimentation, and that if we wanted to be able to use data effectively, until we drop the cost of experimentation below a certain threshold, we won't use data at all. So it's very much like an activation function. There's a threshold at which until you meet it, nothing happens. And it's not that analysis would take 10 times longer if you had something 10 times as slow. It's that you will never be able to perform the necessary data analytics workflows until you have reached a sufficient cost performance threshold. So until you can drive down the cost of experimentation, nothing's going to happen. And there are a few contributing factors to that, right? A lot of people in the community believe that there's this idea of a killer app for synchrophasor data, and maybe there is. Hopefully I will be proved wrong, but I believe that this is a false god, because what I really perceive is an ensemble of applications that are driving the value proposition for synchrophasors at a utility. And feeding into that is how very different and niche each utility organization is. So there's not this cookie cutter approach that other sectors can take to get to have killer apps be as impactful as they are. And the other thing too is the industry is very nascent in its use of synchrophasor data for long-term historical analysis. And so no one really knew what we're going to use it for. There's a lot of a priori guesses, right? Here's what we think that it will use, but really we need to experiment. So it's this need to rapidly prototype and evaluate hypotheses drives this notion that if we don't drive down the cost of working with data, nothing's going to happen. Not only will we not work with the data, but we'll never figure out what it is that we're supposed to be doing, or what is the most valuable use case for that data. So I'll also highlight a few of my contrarian opinions that drove us over the last few years in terms of technology. And this is really speaking to the same technology that is under the NI for AI platform that you all will be able to play with and have access to. As I mentioned, it took a first principles approach to realize that this was the right solution. We also deviated from a lot of the contemporary data analytics solutions and went with a platformed approach instead of a siloed application. For example, if you look at something like Breaker Health Monitoring, there are apps out there that do just that. But that doesn't give us what we need. And the other thing, and I can't understate this enough, I can't overstate this enough. Going with a cloud-based approach versus an on-prem approach was absolutely fundamental to our success with our collaborator Ping Things. So this is really important for any of the utility folks out there that are a little bit scared by that word. Don't be. For you personally, it will be career making. For your company, it will be a godsend. So don't be scared. The other notion here that I want to point out is the Synchrophasor community is very focused on real-time operations use cases, as they should be. But I think we approach myopia to some degree because the pace of innovation in the control room is, well, what it is. And at the end of the day, my job was to define a return on investment for Synchrophasors, our Synchrophasor program. So I had to pivot resources to engineering applications, basically business intelligence, things that happen on a slower scale. And this pivot was fundamental to us driving our value proposition forward. And then the last point that I'll make here is a lot of data analytics use cases have a value proposition that's centered around reducing O&M costs. And while that's great, I don't want to poo-poo on that. I actually believe, particularly for a company like Dominion, that if we can move a needle and one needle only, I'd rather move the capital needle. The capital needle is much, much bigger. And in terms of our ability to have a larger impact on the company, our financial performance, or society in general, particularly in a world of renewable integration, I'd rather focus on capital. And I'll touch on this later when we get into some of our case studies. I mentioned before that we'd worked with Ping Things to set us up with the right technology solution for our data analytics program. This is the same technology that's under the NI for AI platform that you all, it's so literally the exact same thing that Dominion is using is what the NI for AI community will have available to it. I'll point out really two things here that are really important for utility perspective. First is that working with Ping Things was basically a one-stop shop for all aspects of this transformation. IT played a minimal role, and because of that, second point is that we were able to go from signing a contract to streaming data and doing analysis in about 4 months. So the pace that we've been able to innovate at is really not a utility pace. It's been transformational for Dominion and for all of the individuals that have been involved in that work. Something else that you'll get a really nice taste of on the NI for AI platform is the interactive human scale data exploration. So I like to think of it as Google Maps for time series data. There's a very intuitive zooming and panning that is really great for analytics workflows. And it underscores a fundamental principle that you should be thinking of when you're working with data. And that is, you must look at your data. It is the first and the 50th and the 100th step in any analytics pipeline. And so the purpose of these tools is just to make sure that any data that you want to see is at your fingertips virtually instantly. This alone has driven some value propositions inside Dominion, particularly in our fault analysis group. And that's, I forgot that I had this slide here. I'm going to skip this. It's there for you guys to take home and read, but just know that the data visualization has accelerated our ability to do fault analysis to improve restoration times. The other aspect of the platform that's really powerful from a user perspective is the ability to write code to do your work, and to bring that code to the data rather than having to download the data to your workstation and do your work there, the sort of traditional MATLAB approach. So in terms of rapid prototyping and analytic exploration, this is just really, really powerful, both for the exploration of new use cases, as well as for more production quality applications as well. So for the exploitation of use cases. So regardless of whether you're a beginner, intermediate, or an advanced user, this is a really great way to work with data. All you need is a little bit of Python knowledge. And honestly, I believe that the platform has some other language plugins as well. I don't want to quote what's there, but I know it's more than Python. I'm a big fan, and that's what we use in our team. Speaking of, when I talk about fast growth, I can talk about it in terms of our team as well. In July of 2019, there was a team of one, essentially, just me. And over the last, well, what are we at now? Not quite 18 months, 15, 16, 17. We're in that time frame there. We grew from 1 to 2 to 3 to where now I have, come November, I'll have 6 full-time people on staff that are only working on these problems, in addition to 2 graduate internships that we bring in each summer. So we have folks that are working on data analytics, some folks that are working on the modeling tie-ins, which there are many, some folks working on data engineering and technology. But at the end of the day, we have some dedicated resources here, which is really exciting. We've also been very busy. So in terms of answering the question of, well, what are the most interesting use cases for Synchrophasor data, at least for Dominion, we've got a laundry list in various levels of technology readiness. And I won't belabor going through these one by one, but I will point out 2 that are on the more mature side that I'm calling here as StatCom control design and dynamic performance characterization. And supporting both of those under the hood are really dynamic analyses of Synchrophasor data. If we recall the original question before the presentation about, can we use these things for more than steady state? So we're looking at oscillations. We're also looking at spectral analysis and mode and damping estimation. And as you'll see, we're not just looking at these in terms of discrete events on the system. We're looking at them in terms of the continuous and ambient data 24/7 across the system. Now, we aren't just Synchrophasors. We also upload event files. Those are both transient events, but also longer-term waveform captures. So we'll do as many as 15 minutes continuous waveform. We have PMU data that extensively covers the network. We've talked about that. We can also ETL SCADA data over from our Pi system. And we're also uploading network model snapshots from our EMS system at a 10-minute interval. So we can do a lot of really cool things with that, and all that's going into predictive grid. And certainly there are some things that we can hope for in the future as well. But today, with the remaining time that I've got, I want to point out, I want to talk about one particular type of analysis in particular, because it's going to be useful for understanding the variety of case studies that we are that I'm going to share with you. And so this is basically our small signal analysis toolbox. And what it allows us to do is to take signals of voltage and current and frequency and angle and look at them over long periods of time, minutes, hours, days, weeks, months, across the system, and understand across the frequency spectrum that is visible, what are the modes of oscillation that exist, what are their energy levels, what are their damping. And so you can see here, bright areas represent modes of oscillation, brightness represents energy level, and then of course time is on the X and frequency is on the Y. And so we look at these things a lot. And I wanna point out, again, like, we're not looking at events. This is ambient data that we're looking at, and there's a richness there that is, I don't want to use the word surprising. We always hypothesized that it was there, but it's really exciting. And being able to look at this kind of analysis at this scale is quintessential big data problem, and is something that we'd only be able to do with our collaboration with Ping Things. So let's jump in and talk case studies, and I'm going to go through these in a little bit of a rapid fire approach, because I also want to crescendo at the end of the talk with a few things that'll get you thinking. So first thing, and these have been scrubbed of specific locations, so I am purposely being a little bit generic, but the first thing is that there's a lot of activity in the frequency spectrum from industrial dynamics. And this is important because we need to recognize that the distribution circuit, not just from a load perspective, but from a generation perspective, is no longer a passive element in the system. And these behaviors need to be quantified because they can potentially interact with each other. So an industrial driven mode of oscillation might not cause a lot of problems in isolation, but imagine a world where you have ubiquitous solar or other inverter-based resources. This could become a problem, not just with the load dynamics, but with them interacting with themselves, which is a great tie-in to our next case study. We're also looking at oscillations from solar sites, both distribution connected and transmission connected solar sites. You can see here there's an 8 hertz mode in the second half of the day here. Now those vertical striations are actually an arc furnace that is close by that's just muddying up the frequency spectrum. That's not bad data. But we see a lot of activity from our solar plants. And this is important because, as I mentioned, as we increase the number of these assets on the system, the proclivity for interaction is profound, and our models are unable to predict it. So we want to do two things. We want to first use the data to improve our grid models so that we can do analyses to second support the interconnection process. So we do all of these other studies to facilitate new interconnections, but now we're going to need to look at the small signal behavior of the system at the point of interconnection as well. Getting into some larger assets, we've also seen a lot of interesting stuff coming from StatComs. So StatComs are flexible AC transmission system devices. They're really meant as compensation devices. And in a world of renewable energy, they are necessary to maintain a level of flexibility and reliability in the grid. So Dominion, or companies like Dominion, are investing a lot in these types of assets, and they aren't cheap. So it's our job to observe their performance and understand if they're working correctly. So in this case, we were able to observe some modes of oscillation that we identified as correlated with loading in the area. And so we realized that the absence of an adaptive gain controller from the StatCom controller caused this behavior. And we were actually able to validate this hypothesis in the field with an in vivo experiment. Basically, we did we made some changes to the StatCom controller in the field while it was still energized, and we're able to observe the results. We were able to confirm that yes, we do need an adaptive gain controller, and we were able to get some insights into what that gain needed to be. While those are StatComs in isolation with each other, there are also StatComs that are nearby each other and can also interact. So here's an example of a pair of StatComs that are actually part of a group of 4. This analysis just happened to include the 2 StatComs. You can see that there are some substantially undamped modes of oscillation that are almost 180 degrees out of phase from one another. And the impact of this is actually pretty interesting in that so these 2 StatComs are fighting with each other, which can cause equipment degradation. But the potential to fight with each other can actually drive down the gains of StatComs to the point where they actually aren't regulating anymore. And in the times that you may need them, they might not be there for you. Now, I am not an expert in StatCom, so I'm quoting some of our SMEs there. So if you have questions about that, I'll have to direct you to them. But the idea here is that these are not nuisance behaviors. These are behaviors that have to be identified and have to be dealt with. Same thing with our SVCs. For those of you that don't know, SVC is sort of a cousin of the StatCom, but it serves largely the same purpose. We've also been looking at those. Same concepts apply here as well. Now, we've been talking a lot about power electronics because of inverter-based resources and StatComs and SVCs, but there's a lot of other valuable assets on the system that we can look at from this perspective as well. In particular, our spinning metal, our existing generators. And so we've looked, in this case, at our hydro plant and, one of our hydro plants, and we're able to observe a fairly constant 2 hertz mode of oscillation that was present whenever the unit was in operation. And what's really interesting about this example is that it wasn't present in any simulation that we run. So what we were able to do was to take the model and perturb it in certain ways so that we could figure out which component of the model needed to be modified in order to have this reflected in simulation. And in doing so, you achieve 2 things. One is you improve the model, but 2, you can also use this approach in a diagnostic fashion, because figuring out which component of the model is going to produce that behavior will tell you which component of the actual generating unit needs to be modified to eliminate it. So there's this really fantastic marriage of data and models for diagnostic analysis, and we're really just scratching the surface with it. I also alluded to the arc furnace in one of our earlier examples, and I'm bringing it up here really as more of a data wrangling example as opposed to anything else. Just knowing that there's lots of other things that are going on out in the system that show up in your data that are potentially going to mask the behaviors that you're interested in. And there are techniques that you can use to eliminate these and still perform the analyses that you want. So just a very, very power systems, signal processing specific example of data wrangling for those data scientist folks out there. And I should say, for those of you that don't know what an arc furnace is, basically it's a place that recycles old metal, old scrap metal. And the way they do that is by putting all of the metal into a giant furnace and basically applying a 3-phase bolted fault to it until it heats up so much that it melts. It's pretty radical. So check that out on the internet if you're interested. And our last case study here is about our nuclear gen and our gas gen. Similarly, we were looking at the dynamics there, and we observed behaviors that really we could only attribute to aliasing. And we ultimately realized that there was some subsynchronous resonance and shaft dynamics, and that's basically 2 contributing factors to it. One is a change in grid conditions that happens on a periodic basis, and also a change in set point at the plant. And we were only able to diagnose this because we turned to our higher resolution data. So we spotted something in our Synchrophasor data, but it wasn't sufficient for analysis. And so we went to our DFRs and we set up timers so that we could capture minutes of waveform data, not from an event, but just from ambient conditions. And then we were able to analyze those and confirm some of our hypotheses. So again, just Sasha spoke to the need for higher resolution data for some aspects of analysis, and this is just a great example of that. So there's a lot of stuff there, and the pace that we're able to churn out these case studies is actually much faster than we're able to metabolize the results back into the organization. And I see that as a win, because previously our use of data was really encumbered. But now the thing that slows us down is really trying to take what we've learned and make the necessary changes, both inside of our organization and with our vendor partners that produce some of these assets that we're studying. Those time constants are not as fast as analysis, but that's just fine. What I'm hoping, though, is that you see that there is, even in just this one particular analytic methodology, a tremendous value in the use of synchrophasors, having the right analytics tools, and then building a team and investing in developing these competencies. So why does this matter? Particularly this analytic methodology that we're talking about today. Well, it really comes down to the elephant in the room, the one big transformation that everyone is trying to achieve in the current times and into the next few decades, and that's increased renewable penetration. And with increased renewable penetration comes the need for increased dynamic compensation devices, which are also and is also challenged by a limitation of traditional solutions. So fewer wire solutions, more complex technological solutions, not just for cost, but for other drivers as well. And in that world, the likelihood that these devices are going to interact with each other on these parts of the frequency spectrum grows exponentially the more devices that you have on the system. So our job is to establish a baseline now and continue to quantify it as it changes over time, particularly as we interconnect each of these new assets. Because when you go to design new ones or you go to place new ones, you'll need to take into consideration the small signal behavior at those particular sites. I think I missed a key point back here. So the other reason that data analytics, particularly with synchrophasors, is going to be so crucial as we move forward is that in a world where the burdens are much greater on the utility for justifying an investment, we may need to provide more evidence to support a particular solution, particularly when a solution might be tens of millions of dollars. So simulations may not be enough in the future. And we may have to use data and data analysis to help justify investments. This is something that isn't happening now, but I perceive could happen in the future. And in the short term, where in the business are things being impacted? Well, certainly we've spoken about the relationship between data and models. So anywhere where modeling is driving a business process, there's the chance for substantial improvements. The other thing, and we've alluded to this with our StatCom case study examples, that if we can observe the behavior of the system at a place where we're going to install a new asset, or we can observe an asset's performance, we can then influence, for example, the controller design of that asset based on real world data. And this notion also extends into the longer term planning world as well. And we didn't give you any specific examples of that today, but this is something that we're actively working on. We're anticipating a world where data-driven planning is really just as basic of a competency as using, say, PSSE to do N-1 contingency analyses. And the last thing I'll note is that our interconnection processes will need to be adapted to take into consideration not just flow violations and not just harmonics, but also small signal dynamics and behaviors in the areas where the interconnection is going to happen. So just another business process that's going to get changed. And to close us out, or to lead into closing us out, rather, I'm sharing all this with you, and I've shared this with a number of other communities now, and really the cat is out of the bag, or Pandora's box has been opened, if I want to borrow the analogy that I use on the slide. now that we know that these kinds of things are possible with data, it's only a matter of time before others start doing it. And once people see how significant it is for making better decisions with our investments and for improving the performance of our assets, then it won't be long after that until it becomes a requirement. So I see a lot of this as a new competitive advantage for utilities. I think it will help them tap into more affordable capital markets when played out at scale. And I think it's going to affect regulation. I think there'll be a point where your ability to analyze certain aspects of the grid with high resolution data is going to be mandated. And so it sort of leads into this idea of a new utility. And if we were going to describe what that new utility looks like, I think there are three characteristics that matter. The first is we're not just going to rely on physics, but we're also not going to throw it away. In all the talk of machine learning and artificial intelligence, we don't want to forget about how much we already know about the way that our system works. So really, I perceive a unification of physics and data in some of the ways that we married them together for diagnostic purposes in some of our case studies. So it's not just power flows, it's also data flows that are going to matter. And at scale, I also think that we'll be able to be more capital efficient, both in the way that we build our teams and the way that we work, but also in terms of the way that we finance our investments. If we can use data to find a better solution than what we can through simulation, then we can repurpose some of the additional funds to help with things like faster renewable integration. And then really, and probably most importantly, in a world where, heck, we really don't know what the next 5 years are going to look like, which is very different than the past. How can we be more adaptable to the external changing landscape? And I think being able to analyze grid performance is going to be one of those. So now you are at a fork in the road, and I'm that older gentleman who's walking down the path there, and you're back here. This is a place where you haven't really decided what direction you or your organization is going to go in yet, or maybe it's more appropriate to use this analogy for your career as an individual. And so I'm hoping that some of the things that I've shared with you today make it clear that the path forward is very good for this type of data, for this type of analysis, for the technology that supports it, and you should move forward with confidence. I'll also give a few shameless plugs. The NASB conference, which both myself and several of my team members will be presenting at, is coming up in early November. Also, again, if you're interested in the NI for AI project, which is the topic of today's, one of the topics of today's tutorial, the website is here. And if you have questions, this is my email address. Happy to take any of those. And one final shameless plug for today, and that is we have a really robust graduate student internship program. And so if there are any students on the call or any professors or any folks that know young people that are looking for the next step in their career, we're generally taking about 10 students across transmission and distribution per summer. And we just posted our internship postings last week. So they are up on the Dominion Careers website right now. And this is just a sampling of some of the universities that we've worked with over the last 10 years or so. So please, if that's something that you're interested in or know someone that is, please send them to the Dominion website. We'd be happy to see their application. So with that, I'm only 4 minutes behind. So Laurel, I'll turn it back over to you. Thanks.